Yay! So this last section is a little weird. It's a completely different topic, so it couldn't be included in the last exam. Um, but it's only one section. So what I'm going to do is go over this, and on the exam, I think there's only one or two questions on the final exam over this. But just so you'll be ready, I'll go over this section, and online, if you just want to get to the good bits where there's the um, final exam review, so you can just know how to solve those, I'll give you the minute marks. So anyway, sequences. All right. So a sequence is a special kind of function where the only valid x values are positive integers. So integers are dot 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 dot. Basically any number, any happy number, whole number, positive or negative. But all I want is I just want the positive versions. So I'm going to cross out all of these, and I'm going to start at 0. Okay? So another word for the positive integers is, we'll say, the whole numbers. Same thing. Okay? So these are the only valid x values. You can't plug any decimals in. You can't plug any fractions that aren't whole numbers in. You can't plug in any imaginary numbers. Only whole numbers. Okay? So because of that, it means that there's actually a first value, second value, third value, and so on. So notice that 0, this is actually my initial value. Okay? There's a very first value that you can plug in. So this means that there's a first value of the sequence. There's a second. I know it seems a little odd with the numbers, but that's my second value. And then here we got third value, and so on. Meaning that there is order. Okay, so with sequences, we have order. With functions, we don't. You can go from negative infinity to positive infinity, and because you can plug in any number you want, there is no specified order. There is no first term. Okay, negative infinity wouldn't be the first term because negative infinity is not a number. But with sequences, plugging in 0 is your first term. Okay, so we encounter sequences all the time. Anytime there's kind of a lineup, okay, where you're given a number, you're waiting in a line. Okay, awards, first place, second place, third place. Um, Parking garage, that's a sequence. How much do you pay for 1 hour, 2 hours, 3 hours? There's no in between. It's just bumps from one value to another. Anyway, I can keep on going. But I know that you just want to watch this video, get it over with. So let's go into the anatomy. So for functions, variables that we use for functions are mostly f, g, h, sometimes capital F, capital G, capital H, things like that. Sequences, though, we use letters at the beginning of the alphabet. So we use A, B, C, and usually we don't go into F, G, H unless it's a special name. In a bit, we're going to get to the Fibonacci sequence, so we're going to use F, but only because it's Fibonacci, and Fibonacci starts with F. But anyway, usually when you're just dealing with generic sequences, you stick with letters at the beginning of the alphabet. And I don't know why I put those there. I don't know. Sorry. That should go there. I'm sorry. Um, Variables used. So for functions, we use x, t. It's kind of really, those are the main ones. You can use whichever variable. When you get to trig, sometimes you'll use you will use theta. But for sequences, we keep it pretty simple. The letter that we're going to use is usually n. Okay? So this is like your x value. So usually when we talk about a specific number, we'll say the nth term. So the second value, I'll say the second term, third term, fourth term, fifth term, nth term if I want to be generic. Okay, if we evaluate them at a specific number, for functions we'll say something like f of 3, or maybe we'll say h of -7, things like that. For sequences though, we don't do that. We don't use the parentheses. We instead do a subscript and then the number. A subscript n. So for instance, we can use a subscript 1, or maybe say we're using b as a sequence, b subscript 3, or if we're using c as a sequence, c subscript 71. So the subscript tells us what number we're plugging in. Okay, so let me go off to the side. If I say a subscript 1, that means plug 1 into sequence A, lowercase a. Okay, 3 means plug 3 into sequence B. C71 means plug 71 into sequence C. So the subscript tells you what you're plugging in. This is a different notation. As far as equations go, you might say f of x. I'm just making something up. So for sequences, same idea. You could see a subscript n equals 2n plus 5. So remember that variable is n. So that's the idea for sequences. They're just special functions, and because they're special, they have a different kind of vocabulary, a different setup associated with them. All right. Anyway, a general term is a generic term for the nth term of a sequence. So I put the little arrow here. That's what we call the general term. So a general term is kind of like the formula, the equation. Okay? So whenever they say find the general term, they're saying find the equation. But anyway, it's just a generic description for any term in the sequence. Usually when you find the general term, we say that we solve the sequence. Excuse me. Because once you know the general term, I can find any value in it that I want. Okay? So plugging in the position n will give you the term a. Good stuff. So if I want to find the first term, it's going to be a1, and that just means plug 1 into sequence A. Anyway, infinite sequences are usually going to be the ones that we're dealing with. Infinite sequences go on forever. Now, usually, I know up top I had it starting at 0. Usually, though, when we start, they don't start at A0, they start at A1. So we just say that this is the first position, second position, third position. I'll put a little fourth position, all the way to the nth position. Okay, oh, I had it right there. Okay, and so all we're going to do, and this is what's on your homework, or on the review. It says write down the first 5 terms of the following sequences. So the first 5 terms are, we're going to plug in 1, 2, 3, 4, 5. So if I plug in 1 into this, 5 minus 2 is 3. If I plug 2 into this, okay, so let me write above it. This is 5 times 1 minus 2. 5 times 2 minus 2. 5 times 3 minus 2. 5 times 4 minus 2. 5 times 5 minus 2. So we're just plugging in the n value. So if I plug in 2, that's 10 minus 2, that's 8. If I plug in 3, 15 minus 2, 13. Plug in 4, 20 minus 2, 18. Plug in 5, 25 minus 2 is 23. That's it. So there's no need to specify the x value. The position in the sequence tells us what we plugged in. So you don't have to write this. This is not needed. The fact that it's the first term means that I plugged a 1 into it. The fact that it's the third term means that I plugged a 3 into it. Anyway, so on the homework, on your review, these are the questions that you're given. Find the first 5 terms of each sequence. So let's find A1, A2, A3, A4, and A5. So A1, just negative 2 plus 7, negative 2 plus 7, negative 2 plus 7, negative 2 plus 7, negative 2 plus 7. And all I'm doing is I'm plugging in the position. So the first position, second position, third position, fourth position, fifth position. So negative 2 plus 7 is 5. Negative 4 plus 7 is 3. Negative 6 plus 7 is 1. Negative 8 plus 7 is negative 1. Negative 10 plus 7 is negative 3. And that's it. These are my values. 1, 2, 3, 4, 5. So if I was writing my sequence out, I could say that A sub n is equal to 5, 3, 1, negative 1, negative 3, dot, dot, dot. Okay, next one, same idea, except now we plug in, there's 2 n's, but it's the same thing. I got B1, B2, B3. This one's a little bit more clunky than the other one. Oh, I'll go down here. B4, B5. So B1 would be 1 over 1 plus 2, which you can look at that and see that's 1/3. B2 is going to be 2 over 2 plus 2. That's 2 over 4, which is 1/2. 3 would be 3 over 3 plus 2. 3 over 5 is 3/5. 4 over 4 plus 2. That's 4 over 6. 4 over 6 is 2/3. And then 5 over 5 plus 2. That's 5/7. And so my sequence, B sub n, is just 1/3, 1/2, 3/5, 2/3, 5/7. Da, 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 da. All right. So on the review, that's really all they want you to do. It's pretty happy stuff. They just want you to plug in 1, 2, 3, 4, 5 into your sequence, and that's it. Now, finite sequences are sequences that stop. They actually have a last term, but that's about it. We're not going to deal with them too much. All right. Alternating sequence. So an alternating sequence toggles back and forth. If you look at this pattern, negative 1 to the n, negative 1's in parentheses, raised to the nth power. If you plug in 1, you get negative 1 to the 1 is negative 1. If you plug in 2, negative 1 squared is positive 1. If you plug in 3, negative 1 to the cubed is negative 1 3 times. Negative 1 3 times is negative 1. And this pattern continues forever. Okay? So there's a pattern that starts with negative 1. And if I add 1 to the exponent, it kind of shifts the pattern over. And so let's check it out. So negative 1 to the n plus 1. If I plug in 1 here, because of that exponent, 1 plus 1 is 2. Negative 1 squared is positive 1. So all this pattern does is it shifts it so that the first term is positive instead of the first term being negative. But there's 2. So this one starts negative, whereas this one starts positive. Again, we don't do much with it, just so that you'll know it when you see it. Oh, be right back. My pizza is about to be delivered. Yum, yum. Be right back. That was yummy, yummy pizza. All right, anyway. So notice here we have write down the first 5 terms of each sequence. This is exactly the same as the others, except now you know what that negative 1 to the n does. This guy, right there. This guy, right there. So even though it looks intimidating, it's just a switch. It just goes back and forth, toggles back and forth. So, a sub 1, this n to the negative 1 to the n plus 1 starts positive. Yep. Then a2, a3, a4, a5. So positive, negative, positive, negative, positive. That's all that does. And now I can focus on the actual sequence itself, because I already got that taken care of. Plus, minus, plus, minus, plus. Okay? So now n plus 3 squared is just 1 plus 3 squared. So times 4 squared, which is 16, times 2 plus 3 squared, 5 squared. So that's negative 25. 3 plus 3, 6 squared, 36. 4, 5, 6, 7 squared, negative 49. And then 8 squared, positive 64. So my sequence, a sub n, could be written as 16, negative 25, negative 36, sorry, not negative, 36, negative 49, and positive 64. That's it. Now the other one, we write it way up here. So the negative 1 to the n starts negative. And so I know that that's what it's going to look like. How do you know if it starts positive or negative? All you got to do is just plug 1 into it. Negative 1 to the 1 is negative 1. It starts negative. Anyway, now that I can plug 1 into here, I have 1 minus 1 over 1 plus 2. That's just 0. Okay, 2 minus 1 over 2 plus 2. That's going to be positive 2 plus 2, not 2 plus 1. That's going to be positive 1/4. Okay, 3 minus 1 over 3 plus 2. So that's going to be 2 over 4. That's 1/2. Negative 1/2. 4 minus 1 over... Did I do it again? I did it again. I don't know why I keep on putting a 1 there. I'm sorry, guys. So 3 minus 1 is 2. 3 plus 2 is 5. So that's negative 2/5. 4 minus 1 over 4 plus 2. That's 3/6. 3 over 6 is 1/2. And then 5 minus 1 over 5 plus 2. 4/7, but it's negative, so negative 4/7. So my sequence is just 0, 1/4, negative 2/5, 1/2, negative 4/7. That's it. That's all you gotta do. Just plug in 1, 2, 3, 4, 5, and write down the answers you get. So the harder part isn't writing the terms out. The harder part is figuring out what the general term is. So finding the general term can be thought of as solving it. Okay? Now again, unless told otherwise, the first position is going to be n equals 1. So when they say find the general term, what you do is you write down the position underneath. And this is basically your x value. And so how do you go from 1 to 2? How do you go from 2 to 4? From 3 to 6? From 4 to 8? From 5 to 10? Notice that it's always double. So the answer is equal to 2 times the position. Whatever the position is, multiply by 2. 4, 2, 3, 6, 2, 4, 1, 2. And so my sequence is just 2n. That's how we write it. And in case you notice, 2, 4, 6, 8, 10 onward is just the formula for even numbers. And so this thing is actually the official, I can't spell, formula for even numbers. Not formula, the official definition, I should say. I can get any even number by plugging in n as any whole number, any integer actually. So if n is 5, 5 times 2 is 10, the answer is always going to be an even number. Anyway, same thing over here. I have position 1, position 2, position 3, position 4, position 5. And this one's a little trickier, just to show you how tricky they can get. But notice this is the odd numbers. Okay, so an odd number is just equal to an even number minus 1. So the sequence here is b sub n is equal to an even number. I already know the formula for that. That's just 2n minus 1. And that's the formula. Notice if I double it and subtract 1, 1 times 2 minus 1 is 1. 2 times 2 minus 1 is 3. 3 times 2 minus 1 is 5. 4 times 2 minus 1 is 7. 5 times 2 minus 1 is 9. And again, this is the official definition for odd numbers. There's some really cool things you can do with this. You use these definitions to prove, like if in math, if you want to prove that even plus even is even, or odd plus odd is even, you would use these definitions to get the answer. But anyway, I don't have time to go over that. Usually if I'm in class, if it was an actual in-person lecture, I would nerd out and then show you how to do those. All right, so we have some more that are a little more complicated. Find the general term for a sequence whose first 5 terms are given. Now these ones are a little more complicated. What you want to do is you want to break them up into numerator and denominator. So my numerator is 5, 6, 7, 8, 9, and so on. My denominator is 2, 4, 6, 8, 10, and so on. I put my positions underneath, starting at 1. And I just got to figure out each pattern. Notice for this first one, 1 to 5, 2 to 6, 3 to 7, 4 to 8, 5 to 9 is always the position plus 4. So that means that my pattern is n plus 4. Okay. Here we did this one on the previous page. This is just the even numbers. This is just 2 times the position, or 2n. So that means that this formula is n plus 4 over 2n. We solved it. Okay. This other one to the right is a little more complicated. One thing you want to notice is that there's 3 things to this. In addition to the numerator and denominator, notice that there's a toggle. There's the alternating sequences. So we have, let's find that first. The alternating sequence, and then there's numerator, and there's denominator. So the alternating sequence, it starts out positive, then it's negative, then it's positive, then negative, then positive. Okay, so which pattern did that? Remember, there was only 2 to choose from. Let me make this a little smaller. Okay, all we had to choose from was negative 1 to the n or negative 1 to the n plus 1. Well, all you got to do is plug 1 into it. If I plug a 1 into it, if I plug a 1 into this one, this is negative. If I plug a 1 into this one, 1 plus 1 is 2, negative 1 squared is positive. Well, this one starts positive, so it has to be that one. Okay, kind of looks, I'll just cross this one out. Okay, so this is going to be the one that we keep because it started positive. If it started negative, you would keep the other one. So now the numerator, ignoring the negative signs because I already took care of them. 1, 4, 9, 16, 25. Again, if I put the position underneath each one, what do you notice about those numbers? So hopefully you'll notice that it's just the position squared. So whatever the position is, you square it. Position squared, 2 squared, 3 squared, 4 squared, 5 squared. So the answer here is going to be n squared. Whereas on the bottom, I have 1, 3, 9, 27, 81. This one's a lot trickier. And so usually what we do is we imagine these as powers of 3, because 1, 3, 9, 27, 81 are all powers of 3. This is 3 to the 0, 3 to the 1, 3 squared, 3 cubed, 3 to the 4. If I put my position underneath each one, remember starting at 1, we can see that it's 3. 3 is there for all of them. And the exponent is always 1 less than the position. Here's 1, so the answer is 0. Here's 2, the exponent's 1. Here's 3, the exponent's 2. 4, exponent's 3. 5, exponent's 4. So it's 3 to the position minus 1, or 3 to the n minus 1. That one's tricky. And so now I have everything I need. I have the alternating, the numerator, and the denominator. So to write out my final answer, I'll write it over here to keep everything on screen. We would say b sub n, pizza, negative 1 to the n plus 1 times n squared over 3 to the n minus 1. And so notice that this pattern is significantly more difficult than the ones that we've done before. But if you break it up into pieces, the alternating comes first, then the numerator, then the denominator, you're able to tackle it a lot easier. Anyway, next up, recursive sequences. So a recursive sequence is a sequence that uses previous terms in its calculation. It must be, the fancy word for this is seeded, with the first few terms. And the special notation that they use here is this subscript notation. So a subscript n minus 1 just means the term before a to the n. Okay? So I know right now it's kind of like, what? So that's why this first example is here to kind of set things up for you. Consider the sequence a sub n is 5n minus 2. And so like before, we can plug it in. Plug in 1, that's 3. Plug in a 2, 10 minus 2 is 8. Plug in a 3, 13, 18, 23. So what's the first term? My first term is 3. What operation, so ignoring the formula, what operation gets you from term to term? Notice that it's plus 5, plus 5, plus 5, plus 5. So add 5. Okay? So the recursive sequence, if we start at 3, okay? So a, and let me see, this is n minus 1. Yeah. A sub n is equal to, well, I'm rushing. Let me slow down. Okay. So we would say that 8 is equal to 3 plus 5. 13 is equal to 8 plus 5. 18 is equal to 13 plus 5. Notice all of these have the plus 5 in common. And the number here is always the previous term. So the formula, I'll write it out, is a sub n minus 1 plus 5. All right. Why am I making it more complicated than it has to be? Oh, I know what to do. So my current term is always equal to my previous term plus 5. So hopefully that makes sense. If you want to get to your current term, you just take the previous number and add 5. Previous number, add 5. Previous number, add 5. So current term equals previous term plus 5. Current term is a sub n. Previous term is a sub n minus 1. That's special notation. And then plus 5. So it turns out that these two sequences are equal. They're just different formats. This is the standard form, or the general form, whereas this is the recursive form. All right. Anyway, we have 4 examples here. Let's see if we can find the first 5 terms of each of these sequences. So, this first one, they always give you the first term. So a1 equals negative 3. Now what this one's saying is that my current term is equal to 2 minus the previous term. So if a1 equals negative 3, a2 is going to follow this formula. 2 minus the previous term. So 2 minus the previous term. A3, 2 minus the previous term. A4, 2 minus the previous term. A5, 2 minus the previous term. So 2 minus negative 3, that gives me positive 5. 2 minus 5, that gives me negative 3. 2 minus the previous term. Notice again that gives me 5. 2 minus 5 gives me negative 3. So this pattern, a sub n, actually kind of cool. It's just negative 3, 5 repeating. Finding the general term for this would actually be pretty tough. But using recursion, we're able to find the answer relatively easily. Okay, let's move on to the next one. B1 is equal to 5, so they give us the first one. And this next one is the current term. Let me write this out. Current term equals 2 times the previous term plus 3. So 2 times the previous term plus 3. 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 So the previous term is 5. 2 times 5, 10 plus 3 is 13. The previous term is now 13. 2 times 13 is 26, 27, 28, 29. 2 times 29, that's 30 times 2 is 60. My brain's off right now. 58, 61. And you do that, that ends up being 122 plus 3 is 125. So B sub n is just 5, 13, 29, 61, 125, dot, 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 dot. Okay. Next one. This one, this is actually a happy one. This is the Fibonacci sequence. So the Fibonacci sequence actually gives you the first two. So notice that this definition is a little different. It says the current term, is equal to the previous term plus the term before the previous term. So we're going 2 in the past. So A1 is 1, A2, so F1. F2 is also 1. Okay, F3 is going to be the previous term plus the term before that. So 1 plus 1. 1 plus 1 gives me 2. So now we're going to do the same thing. The previous term, well, the previous term is just 2, and the term before that is 1. So 2 plus 1 gives me 3. F of 5. And so we can keep on going. This ends up being the previous term, 3, plus the term before that, 2. 3 plus 2 is 5. And so that's the Fibonacci sequence. That's F sub n, 1, 1, 2, 3, 5, and it keeps on going. 8, 8 plus 5 is 13. 13 plus 8 was it 21? Yeah. And then it keeps on going. But it's really useful. Now, Fibonacci, I put this here because this is called the Fibonacci spiral. Kitty. But if you zoom in, it's called the Fibonacci spiral because the size of the squares that make it. So here we have a square of size 1. I'm zoomed in really far, so it's kind of hard to write. There's 2 squares there of size 1. Then there's a square of size 2. Then up here is a square of size 3. Then over here is a square of size 5. Then over here, that's supposed to be a 5. Then over here is a square of size 8. Over here, this big one is a square of size 13. This big one up here, square of size 21. This big one here, 21 plus 13, 3, 4, 1, 2, 3, 4, 34. Let's make sure I got that right. 3, 4, 2, 3, yeah. And then the next one, 4, 5, 65 over here. Anyway, so that's called the Fibonacci spiral. And it's kind of cool to look at. Again, you start out with 2 squares of size 1. On top of it, you put a square that matches that size. And of course, since this is 1 and 1, this has to be size 2. And then you put a square that matches all 3 sides. Now that's 2 plus 1, so this has to be 3. Then you put another square that matches all these sides. Let's pretend that's a square. So that's 5. Then you have a square that matches all these sides. And that's 5, 6, 7, 8. And that's where the Fibonacci spiral comes from. It occurs a lot in nature, the shapes of stuff. What you do is you start, where's you start? Trying to get it. So you start here. here, 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 ooh, here, 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 and it forms like a conch shell type of shape, and it keeps on going. But anyway, so the shape it occurs, the galaxies form the shape. It occurs a lot in nature, so the Fibonacci pattern is studied a lot. Anyway, the last one here, so that was number, or that sequence. So the last sequence here is a Fibonacci style sequence. And so again, we're going to start with C1 is 1, C2 is 3. And this pattern here is a little different. Let me actually change it. That's a typo on my part. This should say C sub n. This should say n minus 1, and this should say n minus 2. I forgot to change it. So my current term, C3, is going to be 2 times the previous term minus 3 times the term before that. There's my previous term. There's the term before that. So I get 6 minus 3 is 3. I go to the next one. 2 minus 3. So 2 minus, what was green? Or 2 times the previous term minus 3 times the term before that. They both just happen to be 3. So I get 6 minus 9 is negative 3. Last one. So I get 2 times the previous term minus 3 times the term before that, which is 3. So that's negative 6 minus 9 is negative 15. So this pattern is 1, 3, 3, negative 3, negative 15, dot, 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 dot. Anyway, so that's Fibonacci sequences. Again, not too bad. You just got to understand how to read them. All right. Almost done. Notice we have just 3 more pages. So close. All right. The next thing is the factorial. I like factorials. Factorial is a sequence where the input is multiplied by every smaller number until we get to 1. We denote this operation with an exclamation mark. So whenever you see the exclamation mark in math, it's called a factorial. Okay? And a factorial, all it does is you multiply by every number less than it until you get to 1. So 5 factorial is just 5 times 4 times 3 times 2 times 1, or in this case, 120. And I left my calculator in the other room. Oh, no, I have my calculator here. So there you go. Tricks are for kids. And so 20 factorial is just 20 times 19 times 18 times 17. Now, it's kind of annoying to type that. The factorial command is actually in your calculator. It's under math. So you go to math. Then you go to probability. And then you go to 4. Okay? Math probability 4. So you get there, and that's your factorial. So let me type in the number. 20 math probability factorial. And notice how huge this number is. 2.432902008 times 10 to the 18. That means that I have to move this over 18 places. So here is just 9. I have to keep on going another 9. So you have to move over and so that's actually a very, very big number. And that shows you how fast the factorial increases. We start off with 5 factorial is just 120. But then 20 factorial, just 15 numbers more, and you end up with this ginormously huge number. Okay? By standard definition, don't question it. 0 factorial is 1. Okay? When you get to statistics, you'll learn why. But for now, just something that you have to just let it go. 0 factorial is 1. Factorial, again, is the current term. And then n minus 1 is the previous term. N minus 2 is the term before that, the term before that, and you keep going until you get to 3, 2, 1. All right, I'm not going to focus too much on the recursive. So, evaluate the following expressions. Okay, so you could be lame and you could type this in your calculator. 25 math 4 divided by 23 math 4. And notice it gives your answer of 600. But we don't actually need a calculator to figure this out. 25 factorial is just 25 times 24 times 23 times 22, and then dot, 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 because I don't want to write all of that. Whereas 23 factorial and notice that a lot of stuff cancels out. On the top, starting at 23, they all have the same thing in common, so everything cancels out. And all that you got left is 25 times 24, which happens to be 600. So look at that, we didn't even use a calculator. 600. Okay. Now, usually if I had more time to go over this, I usually put a problem like this in an extra lab, but because we lost that week, we don't get to do that. But anyway, so notice that this number, you can't do it. If you try to use your calculator, math 4 divided by 105 math 4. Notice that you get error overflow. It means that your number is too big for the calculator to comprehend. So your calculator can't help you, which means you have to solve it by hand. Now, to help us out, I'm just going to write things like this. Let me give this one more room. So 105 factorial is just 105 times 104 times 103 times 102 times dot, 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 3, 2, 1. 103 factorial is 103 times 102 dot, 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 times 3 times 2 times 1. Whereas 5 factorial is 5 times 4 times 3 times 2 times 1. So what we're going to do is we're going to cancel stuff out. Notice on the bottom, 103, 103, 102, 102, meh, 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 meh. 3, 2, 1, 3, 2, 1. So all that we got left now is 5 times 4 times 3 times 2. I don't need to write times 1 because that's just itself. Over 105 times 104. Well, looking at these, I can figure out these pretty easy. And we can use the calculator to help us out. But I know that 5 over 105, math 1, is 1 over 21. So that's just going to be 1 over 21. 4 over 104, math 1, 1 over 26. And so we get our new fraction. Anything times 1 is itself, so we're just 3 times 2 over 21 times 26. And I can do it again. Notice that these have something in common, and these have something in common. I don't need a calculator for that. That's just 1/7. That's just 1/13. So my answer is 1 over 7 times 13. And what is 7 times 13? 91. Yay! So a little work, but we could actually find an exact answer without using our calculator. Cool, cool. Good stuff. All right. Now the last part of this section, which is the part that's on the review. Summation notation and series. So this usually people see this and they get scared. But all a series is adding up a sequence. Excuse me. Okay? But when we add up a sequence, we can start and stop wherever we want. And that's why we need information. This number on the bottom tells us where we start. That's my starting position. Whereas the number up here is my stopping position. And the number on the inside is the sequence being added. Okay? So this generic definition, notice it says add up sequence A sub k from position 1 to position n. That's what this means. Add up sequence A sub k, starting with the first position right here, ending with the nth position right there. So notice we start with 1, and you keep adding the term before the last term and then the last term. Now when you're inside the summation, the variable changes to k. All right. So again, it sounds really scary. It looks scary because you're like, oh, epsilon, rar. But it's actually not too bad. Let's look at this sequence right here. Evaluate the following series. So I have the summation of 2k plus 1. This is going to be the starting position, whereas this is going to be the stopping position. So that means that it's just going to go 1, 2, 3, 4. So if I plug in a 1 into here, I have 2, remember the formula is 2k plus 1, so 2, 1 plus 1, that's 3. The next one, 2, 2 plus 1 is 5. 2, 3 plus 1 is 7. 2, 4 plus 1 is 9. So the answer to this is just 3 plus 5 plus 7 plus 9. And my brain is totally turned off right now. So 3 plus 5 plus 7 plus 9. 24. That is it. That's all you got to do. Okay, so hopefully it's not too scary. You're looking at it and you're saying, oh, that's not that bad. And that's all they want you to do on the review. Just know what it means. So going to this one, I can do the same thing. Notice that this one starts at 3. It stops at 6. So we have 3, 4, 5, 6. So if I plug in 3, I get 3 squared is 9 minus 2 is 7. Plug in 4, 16 minus 2 is 14. Plug in 5, 25 minus 2 is 23. Plug in 6, 36 minus 2 is 34. And all you got to do is add them up. Oh. 7 plus 14 plus 23 plus 34. You get 78. There you go. Okay. Now on the next page, or sorry, not the next page, but these next ones, they're just, on the homework, you have some problems where they want you to work it out. Here, notice this one starts here, then it stops here. On the homework, the way it's going to be written is a little different. It gives you like boxes, and you type in the number. And then it has plus dot dot dot, and then another one. And then a final one. And so what they want you to do here is starting at 2, plug in 2, plug in 3, then stuff happens. The last term is n plus 1, because that's what they told me. Stop at n plus 1. Okay, 1 less than n plus 1 is just n. Okay, so let's plug it in. So you're going to have 4 boxes on the homework. You plug in 2. 2 plus 1 is 3. 4 plus 2 is 6. So 3 over 6 is actually 1/2. Plug in 3. We get 4 over 7. Plug in n. We get n over n plus 4. Plug in n plus 1. Notice that you get n plus, let's see, oh, I forgot the 1 here. Silly me. We get n plus 2 over n plus 5. So that's what they want you to do in this part. Now, I've been mentioning the homework. I am going to post a homework. It's going to be bonus, though. It'll be fun. Okay, so one more. Let's do this one. This one starts at 0, which is actually something that can happen. And this is where it stops. So it's going to look like the same thing. We're going to have a blank here, plus a blank there, plus dot dot dot, plus a blank. And actually this is going to be a little more room. Plus, and then a final blank. And the numbers we're going to plug in, we're going to start at 0. We're going to plug in 1. And if the last thing is n minus 1, 1 less than n minus 1 is n minus 2. And so we just plug stuff in. If I plug in a 0, I get negative 1 to the 0 is 1. 0 plus 1 is 1, so that's just 1. If I plug in a 1, I get 1 plus 1 is 2. Negative 1 to the 1 is negative 1, so that's negative 2. Here, if I plug in n minus 2, okay, what do we get? Well, negative 2 plus 1 is negative 1. So I get negative 1 to the n minus 2, then parentheses n minus 1. And then for the last one, I'll write it up here. We have negative 1, but this time I'm plugging in n minus 1 to the n minus 1 plus 1. Negative 1 plus 1, they cancel out, and you're left with negative 1 to the n minus 1 times n, because those kill each other. So all I did was I replaced all the k's with 0. I replaced all the k's with 1. And then more generically, I replaced all the k's with n minus 2. And then I replaced all the k's with n minus 1. And sometimes you'll be able to cancel stuff out. All right, last page. Okay, so we have two examples. They just want us to express the series in summation notation. All right. We have a numerator and a denominator, and it's up to you where you want to start. Remember that when you have the summation, you have k. It's up to you where you want to pick it. Now I'm going to keep it simple, and I'm going to start at 1. So here's 1, 2, 3, dot, 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 dot. Now if this is 1, notice that it matches the numerator. That means at the very end here, if the numerator is 13, this has to also be 13. So we have the summation. This is where we started. Oop. This is where we stop. So the summation from k equals 1 to 13. And then we just have to find out the pattern. For my numerator, it's 1, 2, 3, dot, 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 13. And for my denominator, it's 2, 3, 4, dot, 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 14. So if this is the first position, second position, third position, 13th position, the formula for the numerator is just the position, which is just n. For the denominator, remember it's positions 1 through 13. For the denominator, notice the denominator is always 1 more than the position. So this is the position plus 1, or n plus 1. So now I have my two parts of the inside, but when you plug it in on the inside, you have to make it as a k. So instead of n over n plus 1, I'm going to put k over k plus 1. Nope. Okay. Come on, screen. But that's it. That's my expression in summation notation. So I started at 1. I ended at 13. So that's why it's 1 through 13. The pattern for the top was just exactly the same as what the position was. So that's why it's just k. The pattern for the bottom was always 1 more than the position. So the position plus 1. Right? There are other ways to write it, but I'm going to leave it there. Let's go to the last one, and we'll be done with this section. So this part, a little more complicated. Actually, it's not too bad, because they give us the formula. I'm going to start out with position 1, position 2, position 3, position 4. And here, if the bottom corresponds to the position, come on. Then that means that this has to be position n. So this is where we start. This is where we stop. Now, the good thing about this is that they give us the formula. We just have to turn it in a case. So this is the summation from k equals 1, the starting point, to n, the stopping point. And then there's your formula. -1, but you replace them with k's. K minus 1, k minus 1, all over k. Right? Notice that if you plug a 1 into there, you'll get 0 over 1. If you plug a 2 into there, you'll get -1/2. If you plug a 3 into there, positive 2/3. Anyway, so sometimes you'll have to figure out the formula yourself, like in that first one. Other times they'll just give you the formula. But the biggest skill here is knowing where to start and where to stop, and that's the bottom and top of your summation. Anyway, that's it for this lecture. As far as what you need to know for the final, you need to know how to evaluate this series. So know how to do these two. And know how to create the first 5 terms of a sequence. Excuse me. So given a sequence, can you find the first 5 terms? All right. Have a good one, guys. It's been a pleasure being y'all's teacher. I know this has been really crazy and really weird, but yep, it'll be something y'all remember forever. All right. Y'all have a good day.